Okay, now let's get started with vector multiplication and vector product. We have studied scalar product form of vector multiplication. Now we're going to study vector product form of vector multiplication, in which when we multiply vectors, we'll get a vector. Previously, when we used to multiply vector, we used to get a scalar. Let me quickly set a context for this. Now this context doesn't have to do anything with what we are going to study immediately. What I'm going to tell you will be a glimpse of what we are going to study later in the course. So this is just for having a little bit of feeling and not for pure understanding. See, when we have a stick hinged at this point, such that it is free to move like this, and we apply a force F from a distance R of the hinge. Now from our experience, we know, and you must be knowing, when you have a door and you open the door from the extreme end, then you have to apply a little force compared when you open the door from the point very near to the hinge. If the door is like this and you apply a force here, you can open the door relatively with ease. But if it is hinged at this end and you go near the hinge and you try and apply a force from your thumb, and it will be very difficult to open the door. I don't know if you have experienced this or not. If you have not, you just try this thing. Opening the door from the other extreme would be easier, much easier. Because there's a thing called torque. And that torque is force into distance from the hinge, perpendicular distance. Now, when the perpendicular distance increases, then the torque increases. Torque, represented by tau, is force into the perpendicular distance from the hinge. So when you go very near to the hinge, then the perpendicular distance from the hinge decreases, this R decreases. So to open the door or to have the same amount of torque, this force has to be much large if R decreases. That's why opening the door or applying the same amount of torque becomes difficult when you move very near to the hinge. But this is something that we are going to study some days ahead from now. What's important here is we require a thing called vector product here. I'll tell you why. See, instead of applying the force perpendicular to the rod, suppose you applied it obliquely at an angle, a force like this. Then again, to analyze the situation, you should resolve this vector parallel and perpendicular to the rod, something like this. If you resolve the vector, you would realize that this component of the force that you're applying is not helping in moving the rod. Actually, this component will try and pull the rod in this direction. It will try to unhinge it. It will try to break the rod. In case of door, it will try to break the door. This component will try and push the rod, isn't it? This component is a waste if you are concerned only with the rotational motion of the rod. So only this component should be taken into account while calculating torque. Okay, but if we are dealing with the entire force, if I don't have the values of both the components, I just have this value, then the thing is, or suppose this is the angle theta with the rod, then what we are more interested is in the component of F sine theta. We are not interested in F cos theta, which is this. We are interested in F sine theta because F cos theta is not helping. It is only the component F sine theta which is helping in bringing about rotational motion in the rod. So F sine theta is what I require. I don't require F cos theta. So what I require, so now when you calculate torque, what we do is we just take into account F sine theta and the distance R. So what we have is Fr sine theta. And as you can feel from here, just as we define dot product A into B cos theta, we are going to define a cross product A into B sine theta. But since this is a vector product, it will also carry a direction with this. The direction of this I'll tell you in a while, but for the time being, A cross B, we brought a dot between A and B there. We'll be bringing a cross between A and B here, and this is for the same reason it is also called as cross product. Now A cross B will be equal to A into B into sine theta. If I have this kind of definition of cross product between A and B, that A cross B is equal to AB sine theta, then torque I can always write as torque is F cross R, right? Because F cross R would be F into R into sine theta, and that is what you require actually for calculating torque. Can you see? You require F sine theta, and you will get F sine theta automatically from this definition. So there are some physical requirement of defining such kind of cross product. So we define it, but this torque and whole thing you just forget about for the time being, because we are not delving into it. Our prime motive here to understand cross product, and with a little bit of feel we have understood that there is a need for defining such a quantity, and A cross B is defined as A into B into sine theta, theta being the angle between A and B. Now there's a direction of cross product, and the direction would be, suppose A vector and B vector are oriented like this, and this is the theta angle between them. Now learn this quickly. Do as I do. Now take out your right hand and stretch all your fingers like this. Do it along with me, otherwise you will not learn. Now you point your hand towards B vector, towards A vector, A cross B, then whichever vector is coming first, you point your thumb, you point your entire palm through that vector, in the direction of that vector. Okay, now you have to keep your thumb perpendicular to rest of your four fingers, all stretched outwards, like this. Okay, now what you have to do is you have to curl your right palm from A to B. Now if you keep your hand like I have kept, then you will not be able to curl, because naturally you will curl in this direction. You can't curl in this direction. So in order to go from A to B, you have to keep your hand like this. Now you can curl your right palm from A to B like this. Now when you do that, in whichever direction your thumb is pointing, that is the direction of A cross B. For instance, in this case, if I curl my right palm from A to B, my thumb is pointing downwards. So the direction of A cross B would be downwards. I'm representing it by a general vector n cap, and I'll tell that n cap is actually downwards. This is how you find. Okay, now let's have a very quick practice on this. Suppose this black marker is A vector, and this red marker is B vector. I have to find A cross B. How would I do it? I'll take my right hand, stretch all my fingers outwards, keeping my thumb perpendicular to the rest of the four fingers. Now what I have to do, I have to go from A to B. This is A, this is B. Go from A to B. If you keep your thumb, if you keep your palm like this, you can't go from A to B naturally. Naturally you will curl like this. So keep your palm like this so that you can go from A to B naturally. Now your thumb would be pointing, like my thumb is pointing in this direction. So this is the direction of A cross B. If this is the orientation and this is A and this is B, then A cross B downwards. If this is the orientation, this is A, this is B, then A cross B upwards. Okay? This is called right hand thumb rule. They will generally write in the book right hand screw rule, and it's actually just the same. I think this palm rule is easier. You always apply this. This is quick and fast. So this is the thing. This is how we define A vector and B vector. This is how we define the vector product of two vectors. We read it as A cross B because there's a cross between A and B. This is also called as cross product, and this is A B sine theta, having the direction defined by right hand thumb rule, which we just saw. Now certain observation related to this vector product. Observation number one, as you can, on the merit of the discussion we just had, the vector product will be perpendicular to both the vectors. Now because if these are the two vectors, now two vectors will always be in a plane, whatever the orientation be. You can always get two vectors in a plane. Bring two vectors in one plane. They will always be in one plane, whatever the orientation be. So, and the vector product is actually perpendicular to both of them. Because in the right hand thumb rule, what we are doing, we are bringing both of the vectors in one plane, and we are curling our palm from one vector to the other, and the thumb is giving us the direction of the vector product. Now thumb will be perpendicular to both the vectors in that case. Actually it will be perpendicular to the plane. The plane in which we are curling our palm, the thumb will be perpendicular to that plane. The vector is lying in that plane. So the vector product is actually perpendicular to both the vectors, whatever the orientation be. So later on you will see that it's a very good method of getting a vector perpendicular to two given vectors. You do the cross product and you get a vector perpendicular to both the given vectors. So the A cross B is perpendicular to both A vector and B vector. This is the first immediate thing that you would realize from the definition of cross product. The other thing is A cross B is not equal to B cross A. For the reason you would understand that A cross B, suppose the black one is A, then A cross B, if you're curling your right palm from A to B, your thumb is pointing downwards like this. And if you are curling your palm from B to A, then it's just in the opposite direction. So the magnitude will remain same. Everything is same. A magnitude of A, B and theta, they all are same, but the direction will vary. And vectors have both the components magnitude and direction. If direction changes, the vector changes. So A cross B will not be same as B cross A. Rather, A cross B will be negative of B cross A because the direction is just opposite and the magnitude is same. Okay.